not going to, I've just gone on with it, so.
So what we're going to do is now talk about reflection and refraction. And well, let's press on. So you still have, well, we're going to have this z-axis, x-axis. This is medium 1. This is medium 2. Yeah? You have an incoming wave, and with an electric field that has to be transverse, so it is this direction. And we're going to see how reflection and refraction takes place. So this is a special case. We'll study the more general case shortly. This is just, so the difficulty here again is entirely algebra, just keeping track of boundary conditions. So this is normal incidence. And what are we trying to study? Reflection and refraction. So let me begin, as always, with boundary conditions. There are no charges that have been deposited. So the right-hand side of boundary conditions is 0. So this is coming with some V1. If you want, this is just going to be air and water, if you will. So this will be just C in magnitude. But we want to consider the case where it is water to air as well. So let me write down the boundary conditions. This is my normal direction. So it is epsilon 1. We don't know if it's epsilon naught. Epsilon 1 could be epsilon naught, but E1 perp minus epsilon 2, E2 perp must be equal to 0. And B normal is continuous. This comes from divergence, so B is 0. This also comes from divergence of D equals 0, because there are no free charges. And now the parallel equations, E1 parallel equals E2 parallel. And the only difference is with this mu and epsilon. It is D and H that is continuous. So because it's D, you get the epsilon. It's continuous because there are no free charges. So this is B1 parallel minus 1 over mu2, B2 parallel equal to 0. Remember, this is actually, it is 0, but it is free current. That's the actual boundary condition. But for us, there's no boundary, current vector, surface current. That's the reason it is 0. So what we're going to do is send an initial, and these are, I'm going to stop, let me do it once and I won't do it again. So these are complex waves. So all of these things are complex, so I don't have to worry about a phase factor at all. It'll be absorbed in the complex part. And we're considering normal incidence. That means E is, so this velocity vector is perpendicular through the surface. That's what I mean by normal incidence. So this is the interface between the two materials. Yeah? So I can pick my incoming wave, and I pick it to be E0 I, again, complex e to the I k1z minus omega t in the x hat direction. I can choose this because this is an incoming wave. I can choose which way the incoming wave should be. I could have picked x or y, I just picked x. Yeah? It has to be perpendicular to z because these waves are transverse. So then, the moment I do this, I'm fixing this. And tell me why I get this. Where did this expression come from?
Another relationship between these and these.
Yeah, that's it. That is where it comes from. So the direction of k, which is z hat, cross x better be y. And that is true because I do z cross x as y. Okay. Now, some of it will get reflected, and I'm already dropping the complex part. So this will be justified, well, there's E0R, e to the I, k, it's reflected, so it is, let me explain this. We have, and this is also x hat. Oh, there are a few things. Minus. You know why it's minus? Because this is incoming. Yeah? The reflected wave is going the other way. We don't want the omega to be minus because otherwise the boundary conditions will not be satisfied at all times. Yeah? So that's why we want omega on both left side and right side to be the same. So I get the minus part. Why did I pick the numerical number k1 to be exactly the same as this? Because of this formula. Velocity in any medium is omega over k. Omega is the same. Speed of the electromagnetic wave is the same. So the magnitude better be same as k1. Yeah? So the only choices here are plus k1 or minus k1. We picked minus because it's pointing the other way. There's a little bit of a cheat. If I have an incoming wave oscillating in the x direction, how do I know the reflected wave doesn't flip to the y direction or somewhere in between? So this will be justified in the next section we're going to do. There are nice features about reflection and refraction, but let's assume that this will satisfy all the conditions for now. It'll be justified very soon. But once again, what do I get? Minus E0R over V1 e to the I, oops, e to the I, minus K1Z minus omega T y hat. Is that true? Correct.
So why do we have a sign put on the amplitude for the negative?
Oh, right. K flips.
Oh, yeah.
K becomes minus K. So look at this diagram. Here, this becomes that's my E, and this is my correct? Now here, this is yeah? I don't know if E0I is plus or minus. We'll have both cases depending on which one has a higher refractive index. But suppose my reflected E is like this. So this is E reflected. Then what do I know? I know that B is going to be into the board. I am not saying, however, that if initial incoming E is pointing in the plus X direction, that this will also be in the X direction. I'm not saying that. But relative to this, this would have flipped. If E is in fact negative, then B would continue to be in phase. Yeah? And you know the story from before, right? When one is denser than the other, if the incoming region has a less dense string, it does not flip. But on the other hand, if it has a higher density, then it flips. Same thing here, the same agreement. These are exactly the same thing. Okay, fine. Now let's do the transmitted part. E transmitted. What do I not know? Oh, there are two things. First of all, this is K2, C minus omega T. And BT, what is it? E0T over V2. E to the I, K2Z minus omega T, Y hat, and yep. Problem is, I need all of this to now impose the boundary conditions. But, you know, space, unfortunately, is not expanding on this side of the board, so I'll have to erase this. So let me also clarify this feature. So first of all, I would have this one, V2. This is my E transmitted, and B transmitted. And another important feature, these two at the moment are what we would call an ansatz, which means we're guessing the form. If it works out, fine. We'll prove this. In the next section. Incoming, I have a choice. The direction of E, I can call that X. Reflection and transmission, I don't have a choice anymore. That depends on the physics. But we have chosen this. So technically, that's a cheat. So what I'm going to do is take all of this and impose these conditions. Let me keep these conditions here for the moment. I'll have to erase this. So put that in your memory here.
And by proxy, the B hats are connected to that same, because they have to be, so they're all connected to that state.
Correct. Once this is fixed, I don't have a choice on this one.
Yeah.
Yeah. So this is no longer a guess. This is my guess. Yeah. Okay. So like I said, I'll have to erase this part. So the first one is, yeah, this doesn't, let's see, yeah, this doesn't even exist. It's a transverse wave. It's this one, right? So now let me write it as a complex one. E0I plus E0R is equal to E0T. This doesn't exist. So it is this one. 1 over mu1, I have 1 over V1 E0I minus 1 over 1 E0R equals 1 over mu2 V2. Is that correct? Yeah. Check. Question.
Can you go back to why you decided to chose the ones that you chose to use?
Oh, this is the component of E perpendicular to this surface. That is this direction. But E is no, this is the component in this direction, but E is in this direction. So same thing with B. E and B is in the XY plane. The normal is in the Z axis. E and B has no components in the Z axis. So we're actually not using this. We're only using these two. So because of this mu1, I have mu1 over here. This is equal to 0, so I brought this to the other side. I have mu2 over here. And because of the reflection, it flips sign. Yeah? So I'm going to, I can write this as E0I minus E0R equals beta times E0T, where beta is mu1 V1 over mu2 V2. There's a common factor mu1 V1. Yeah? So I have this plus this and this minus this. This is just easy to do. When I add them up, what do I get? I get, if I do 1, 2, 1 plus 2, well, on one side it gives me 2 E0I is equal to 1 plus beta E0, 1 plus beta E0T. Yeah? And so what I need really is E0T in terms of E0I. Make sure. Yep, 1, 2. Transmission in terms of the internal object. Once you get transmission, you can go stick the transmission anywhere you want and solve for the reflection. Correct? I'm not going to do it. I'm just going to write the result. E0R is 1 minus beta over 1 plus beta E0I. Correct.
And V2, or V1 is what we kind of control because that's our incoming. V2,
Yeah.
V2 itself is like figure out V2 before we do it.
Right, well, in some sense it's given to you because you know what the material is on the
Yeah.
other side.
Yeah.
Okay, so for most materials that we're interested in, mu2 is the same as mu1. The water and glass is dielectric. It doesn't have a magnetic feature to it. Yeah, it doesn't. So So, beta is nothing more than,
This would be the case if we're going from air to water.
it would be the
It would
case.
still be the case.
Yeah, I mean, because air and water does not have a magnetic dipole moment. Air and glass, air, water, and glass, different kinds of glass, different polymers, plastics, for example. These are the usual translucent objects. But if not, the complexity is only algebraic. Just leave that in there. Yeah? Okay, so now, done with the boundary conditions, we can do a little bit of simplification, and then for example, what is 1 minus beta over 1 plus beta? It's 1 minus, what is beta? Beta is V1 over V2. Isn't that just V2 minus V1 over? So then I would have E0 R is equal to V2 minus V1 over V2 plus V1 E0 I. We can immediately say in real numbers E0 R is equal to V2 minus V1 because yeah, that's what it is. Because the amplitudes are positive. So if V2 is greater than V1, then ER is in phase with E0I. If V2 is greater than V1, then E0R is in phase, well, I should say this one. ER is in phase with EI. For example, light going from, you tell me, air to water or water to air? Think about this. Correct. Because air has a higher speed. Air is practically vacuum. And what about the other case? It is out of phase by 180 degrees. V2 is less than V1. Then ER is out of phase by 180 degrees as compared to yeah. So that means if this is water and air, this diagram is correct. If this is air and water, this would have flipped and B would have come out. That's what it means. Let me also write the expression for, I think I erased all of that, but E transmitted. Transmitted is always nice. It is in phase all the time. Nothing going on. Note, so if this is true, watch it guys, then I can say this is true, because this is all positive, there's no subtraction. V1 and V2 is the speed, not the velocity. Oh, the directions have been taken care of by K. It's not so difficult to show that also E0R can be written this way. I'll show you how. Let me 2 and 1. That is not difficult to see because what is V2? Or V is nothing but C over N. Yeah. Yeah, so I think this is trivial. V equals C over N. So V1 is C over N1, V2 is C over N2. You just stick that in there, all the C's get canceled off, and you get an expression in terms of N1 and N2. Fine, but there's a nice little story to this. We talked about intensity. Let me make sure that is correct. Yep, it is correct. So we did this in vacuum. So in a media, it is 1 over 2 epsilon V E0 squared. So I will need this expression. I'll need this or this. I'm going to use this one. What is intensity? Power per unit area. Pressure as area in it already.
Yeah.
Energy crossing a surface per unit area per unit time. But in some sense, what goes in must come out. So you must need a conservation. So I'm going to define reflectance. This is the reflectance. This is defined to be reflected intensity over the incoming intensity. So if reflection and incoming is both in V1, so I would get 1/2 epsilon 1 V1 E0R squared divided by 1/2 epsilon 1 V1 E0T squared. Therefore, reflectance is just E0R over E0I squared, and that is what? N1 minus N2 squared over N1 plus N2 squared. Okay? What do you think? This is going to be defined as? Yep. Now it's tricky. It is epsilon 2 V2 over epsilon 1 V1. And then, did I use the right expression? Correct, I did. Correct? I want to simplify this guy, get rid of any mu dependence. I can slightly cheat. Why can I cheat? Mu2 is roughly same as. So then this is nothing but 1 over V2 squared, and this is V1 squared, and then multiplied by V2 over V1, and then I get what? V1 over V2. And I think I write it in terms of N2 over N1. Because V is C over N. So then, transmittance is N2 over N1 divided by 2, so I square it, N1 squared over N1 plus N2 squared. So that is 4 N1 N2 over N1 plus N2 squared. Yeah? I know we're just plugging along. I know it's just algebra, but there's good physics in here. I'm going to get to the point, but so that we don't confuse ourselves, any questions? So what I'm going to do is n1 squared plus n2 squared minus 2 n1 n2 divided by n1 plus n2 squared plus 4 n1 n2 over n1 plus n2 squared. And lo and behold, I get n1 plus n2 over n1 plus n2 squared, thereby getting a nice conservation. Because these are ratios of the incoming intensity. So the reflected plus transmitted is, in other words, the reflected intensity plus the transmitted intensity is exactly equal to the incoming intensity. Any questions? All the boundary conditions work out. So our form of expression for E, one could argue, well, we guessed correctly, because in physics, a unique past should determine a unique future. If we have more than one, well, in classical physics, yeah? So we cannot have another one. That is one argument, but that is hardly an argument. That's just wishful thinking. We'll in fact show that it is true. What's the difficulty? I assure you, only algebra. So the next lecture, we'll be talking a good bit of algebra. It is annoying, but there are so many great features. I hope it also culminates in a demonstration. So here's what I'm going to do next time. I'm going to have an incoming wave. This is incoming. I'll have a reflected wave, and I'll have a transmitted wave. I drew this diagram with air and water in mind, and so that angle of incident looks like it's equal to an angle of reflection, but the angle of transmission is different. We better get Snell's law. N1 sine theta 1 equals N2 sine theta 2. Turns out that really doesn't depend so much on the exact form of Maxwell's equations. This is just wave properties. Yeah? Maxwell's equations will have to govern the reflectance and the transmittance and things like that. In this example, I will in fact show that if initially E has that X component, then all the E's will not have a Y component. So our form, the ansatz, would be justified. I know I'm a bit early, but I would hate to set it up and not take you through anything substantial. So I'm going to end 9 minutes early.